Part 5 deals with graphing word problems, and the first problem, they're giving you two equations which represent the amount of money spent on books in billions of dollars in the United States. So what you need to do is you need to graph both equations from the year 2000 to the present, and they tell you that x equals 0 corresponds to 2000. So we're graphing from 2000, so we're going to let our x min be 0 because that represents 2000. And at the time of this video, it's 2018, so I'm going to set my x max to 18. God help me if I'm still teaching and it's the year 2057, then I would let the x max be 57 to represent 2057. As far as the y's, though, go, we don't know what y, the amount of money spent in billions of dollars, is from the years 2000 to 2018. So what we're going to do is we're going to enter these two equations into our graphing calculator, and then we're going to use the table to see the range of values for y when x is between 0 and 18. So when I went to my table setup, I went to second and window. I started my table off at 0 because that's the year 2000. And I decided to go up by 3s because I wanted to see from 0 to 18, and I wanted it to fit on the same viewing screen for my table. So I went to second and graph then, and this is what the values turn out to be. And I need to make sure, I need to choose a y range to make sure that all these values for the two y's, when x ranges from 0 to 18, I need to make sure that all these values for y's fit on my screen. So I'm going to set my y min to be 0, because the amount of money spent on books you wouldn't think could be negative. But here the biggest value that I see from 0 to 18 looks like is this 61.7 number. So I'm going to set my y max to be 65, and that'll ensure that all of these values then fit on my graph. So now I'll press graph, and here's what my graph looks like. What we need to do in part B is find the 2 years when both equations predict the same amount of sales. Basically, you're being asked in part B to find the points of intersection of these two equations. And it appears that there are two. It looks like there's definitely one about here when the two lines meet, and there's also a point about here. So let's go about finding the points of intersection. We do that by going to second and then trace for calculate and going down to option 5. And what you're going to do is you're going to press enter twice, first when it says first curve, then when it says second curve. And then the key is when the calculator then says guess, you have to, using the arrow buttons, move the cursor closer to whichever point of intersection you're trying to find. So since my cursor is about here and there's a point of intersection about there, then what we're going to do is just press enter, and my calculator will give me this point of intersection. I'll have to repeat the process, but then when it says guess, move my cursor closer to this point of intersection, so that way my calculator gives me that point as well. So here are the 2 points of intersection, and you're being asked to find the 2 years when both equations predict the same amount of sales. And we have to round to the nearest year for each, so the years are the x's. So here 1.7, so that would be the year 2, and 8.1, that would be the year 8. And remember, x equals 0 corresponded to the year 2000. So in this case, it's going to be the years 2002 and 2008. Letter C, the actual money in billions of dollars spent on books. Remember, these equations represent approximations for the amount of money spent on books. That's what we do in math. We try to come up with approximations for actual values. Here it says the actual money spent in 2006 was $25 billion. Which equation gives the better approximation in the year 2006? So in order to do that, we're going to go to our table, let x be equal to 6, and see the two equations approximation. So here we go. Equation 1 gives the approximation of 24.322 billion, and equation 2 gives the approximation of 25.2 billion. It says which equation gives the better approximation, so which one is closer to 25 billion? Well, equation 1 is 24.3, so this one is about 0.7 billion away. Equation 2 is 25.2, so that's 0.2 billion away. So which one is closer? It looks like here equation 2, and it says how far from the actual value is the better approximation to the nearest million. Well, equation 2 is 25.2 billion. The actual value is 25 billion, so when I subtract, I get 0.2 billion. But this one says which one gives the approximation to the nearest million of dollars? Well, 0.2 billion, if I take 0.2 and multiply it by a billion, that's going to give me in actual values 200 million. So how far to the nearest million is this approximation? It's 200 million away. Again, how did I do that? I multiplied it by a billion because our values were given to us in billions. Problem 2 gives the amount of sales for a company in thousands of dollars by this equation, and you're being asked to graph the following from 1985 to 2017. So your X-min is going to be 1985, your X-max is going to be 2017, and here you're told that 0 corresponded to the year 1990. Well, 1990 is between those two years, and here our X-min is going to be -5 because 1985 is 5 years prior to 1990. Well, what's our X-max going to be? Well, from 1990 to 2017, if I subtract those two values, here you're going to get 27. So here we need to set our X-max to be 27 to correspond to the year 2017. Now, Y represents the amount of sales, and I don't know how many sales this company has done. So what I'm going to do is I'm going to enter this equation into the Y equals screen and go to the table and look once again in between -5 and 27 to see what the sales correspond to. So here, if I get creative and look at my table, in the year -5, sales were about 10.9. Now, this particular question happened to mention that this is the sales in thousands of dollars. So I go from 10.9 all the way up to the year 27, which is that 666 number. So what I'll do is I'll set my X-min to be 0, and for my X-max, I'm going to choose a number that's just bigger than that 666,000 number. So maybe I'll set my Y-max, that is, to be 700. So I'm going to go from -5 to 27 for my X-min and my X-max, because those correspond to the years given to me in the problem. And then Y's, the Y-min and the Y-max, you have to choose values that make the values from the equation fit on your graph. So here's what our graph looks like. So here's my graph. And for part B, find the amount of sales the company had in the year 2005. So since x equals 0 corresponded to the year 1990 that was given to me in the problem, if if I go 2005 minus 1990, that would correspond to the year x is equal to 15. So I'm going to go to my table and look at the value for y when x is 15. So here it's going to be 493.3 thousand. So we can either write our answer as 493.3 thousand, or what's probably better mathematically is if we just take 493 and 0.3 and multiply it by 1,000, or just move the decimal point 3 places to the right. Here the sales are going to be 493,300. Letter C, we have to find the year to the nearest year when the sales of the company hit a relative minimum. Now, a relative minimum is a point where the points immediately to its left and to its right are greater than. So, for example, down over here is the absolute minimum on this particular graph. If we're graphing from 1985 to 2017, this is the absolute minimum. Obviously, the graph continues to the left, but we only had to graph between these 2 years. So this is the absolute minimum. But it looks like there's going to be a point somewhere in here where the sales bottomed out. They kind of reached a high point, then decreased, and then increased after that point. So this point here is what we call in math the relative minimum. So how do we go about finding that? We go to second and calculate, and option 5 for minimum. Just like before, we have to give it a left bound and a right bound. So hopefully you see on my graph, I chose my left bound to be here, my right bound to be here. So now my calculator is looking in between those points for that relative minimum. And then when it says guess, all I do is press enter. And here's what my minimum turned out to be. And the question said, find the year when the sales hit the minimum and find the amount of sales. So we're going to round to the nearest year. So 16.7, x is the year, so we're going to round to the nearest year, that's 17. So since 0 corresponded to the year 1990, I'm just going to take 17 and add it to 1990, which means the year is 2007, and the sales in thousands of dollars were $491,243.26. Again, how did I get that value? I just looked at the y value for that relative minimum, and I just took it and multiplied it by 1,000 because they told me the sales were in thousands. Part D, the company set a goal for reaching sales of $500,000 in the year 2009. How far from the goal did the company's sales reach? Well, since 0 corresponded to the year 1990, if I do 2009 minus 1990, that would correspond to the year 19. So now go to your table, look when x is equal to 19, look at the y for the sales. So here the sales were 496,276. The goal was 500,000 in sales. So how far from the goal did they reach? If I just subtract those two values, $3,724 away from their goal. The height y of a football thrown is given by this equation, where x represents the horizontal distance in feet from where the ball is thrown. And here I'm given this equation, and It's a parabola because I have an x squared, and since the lead coefficient is negative, I'm going to have a parabola that opens downward. So basically you're going to have a person is throwing this ball, x is the horizontal distance, and y is going to represent the height of the ball. So we're going to have to set up a viewing window, and it says use an appropriate viewing window. So what we're going to do is we're going to enter this equation into our y equals screen, go to the table, and look at the values that we have in our table. X represented the horizontal distance, and y represented the height of the football. And what I did was I kept playing with my table until I saw this pop up in the height. When the horizontal distance is 50, the height of the football is negative 20. And since the height of a ball can't be negative, I figured the ball had to hit the ground somewhere between these two heights. So as far as an appropriate viewing window is set up, I'm going to set my x min to 0 because the horizontal distance can't be negative. The x max I'm going to set it at 50. The y min I'm going to set it at 0. And then it looks like the highest distance, the highest height that I see for the y max, I see a little over 45. So maybe what I'll do is I'll go from 0 to 50 for the y's. So I'm getting 0 to 50 for the y's because I'm looking in the y column at the values that I have. And I'm using 0 to 50 for my x's because it looks like when you get to about a distance of 50 feet, the height of the ball is negative, meaning it already hit the ground. So that's why I'm using this viewing window. And notice this is what my parabola looks like. Letter B, how high is the ball when it's thrown? Now, we have to understand what's going on. We have this person who's throwing the football. It's leaving their hand and following this parabolic path. So the x-axis is the ground. How high is the ball when it's thrown? Basically, you want to know this height right there, the height when the horizontal distance is 0. When the horizontal distance is 0, it hasn't started traveling yet, but that's the height of the ball when it's thrown. So all I'm going to do is go to my table and use the value when x is equal to 0. And here we go. When the horizontal distance is 0, the height of the ball is 4.5 feet. Letter B, what is the maximum height of the ball? Well, in order to calculate a maximum, I'm going to go to Second and trace our Calculate menu, and I'll choose the option for maximum. So here's what our maximum turned out to be. They're asking you for the maximum height. The height is the y value. So here, the maximum height, and the question said to the nearest tenth of a foot if necessary, 45.8 feet. Part D, how far from the person does the ball first hit the ground? So basically, we have to go back to our diagram, and we're trying to find this point right here when the ball hits the ground. Now that's going to be the x-intercept because the ground is my x-axis. That's going to be the 0 of this equation. So I'm going to go back to my Calculate menu and go to option 2 to calculate the 0. So here's the 0. The height is 0 when the ball hits the ground. How far from the person? So they're asking you for the horizontal distance. Here to the nearest tenth of a foot, 45.2 feet. Find the height of the ball after 4 seconds. In order to find that, we're just going to go back to our table and find the value when x is equal to 4. So here's my table when x is equal to 4 to the nearest tenth, 18.1 feet. And then finally, find the horizontal distance or distances when the height of the football is 30 feet in the air. So here they're telling you y is equal to 30 because y represented the height, and we need to find the horizontal distance, we need to find the x. And anytime you are given a y value and you need to find an x value, the best way to do that is to graph the y value. I'm going to graph the equation y equals 30 and then find the point or points of intersection of our equation and this new equation y is equal to 30. So I'm graphing y equals 30 and I'm finding the points of intersection. And here you go, here's the 2 points of intersection. We have to find the x value to the nearest tenth. So it looks like here we're going to have 8.4 feet and we're going to have 35.6 feet.